Today, I'll be talking about a comparison of techniques for language model integration in encoder-decoder speech recognition. The paper is from Toyota Technological Institute and Google. End-to-end automatic speech recognition systems provide an elegant solution to ASR's problems. It folds acoustic model, pronunciation model, and language model into a network and requires only pairs of speech and text for training. But it isn't clear how to use addition and paired text to improve the system performance. One approach is to train external language model on the unpaired text and then integrate the language model to end-to-end ASR model. There are three ways to integrate the language model: shallow fusion, deep fusion, and cold fusion. The three differs in two criteria. First criteria is early or late model integration. The second criteria is early or late training integration. The first criteria answers the question, at what point in ASR model's computation should language model be integrated? Deep and cold fusion directly fuse external language model into ASR model by combining their hidden states. The integration is very tight. In contrast, shallow fusion only combines the score of the external language model and ASR model. In other words, two models remain separate. The second criteria answers the question, at what point in ASR model's training should language model be integrated? Deep and shallow fusion use late integration, where both ASR and language models are trained separately and then combined. In contrast, cold fusion uses external pre-trained language model from beginning of ASR model training. Note that early integration is computational costlier when either of two models is frequently changing. Those previous results show that shallow fusion has largely been the method of choice, while cold fusion outperformed deep fusion in cross-domain setting. However, none of those studies compare all three fusion approaches. The goal of this work is to shed light on how language model integration approaches compare, as well as how they scale up in data science. In the next section, the listen, attend, spell ASR model is revisited. Three fusion approaches are also revisited. Moreover, two new approaches for using unpaired text were presented. In this work, the end-to-end ASR system is based on listen, attend, and spell. There are three main components: the encoder, the attention, and decoder. The listener encoder maps input features x1 to xt to higher level features h. The attention determines which feature in h should be attended to predict the next output symbol. Finally, speller or decoder and softmax takes the attention context C and previous prediction to produce a probability distribution over all support units for next symbol. To integrate the external language model to the last model, or listen, attend, spell model, there are three approaches: shallow fusion, deep fusion, and cold fusion. In shallow fusion, external language model is incorporated via log linear interpolation at inference time only. As a result, we can use either FST-based and-gram language model or neural language model. In contrast, deep and cold fusion generally require an external neural language model. Deep fusion fuse together hidden states of external language models and last models decoder. Last model and external language model are first trained separately. To combine two models, Getting's module is introduced. Both Getting and softmax modules are fed to while keeping other parameters. Getting modules decides when information from external language models should be used. In confusion, external language model is pre-trained. To combine external language model with large model, a DNN module and a getting module are introduced. Everything are trained from scratch while keeping the external language model. In other words, this is an early training integration. Getting modules decides when information from external language model should be used. For example, when output symbol is non-blank symbol. Different from diffusion, both ASR states and language model states are used in gate computation. In this work, the author proposed two methods. The first one is language model as lower decoder layer. The motivation is to provide better contextualized word embeddings. External language model was introduced as lower layer of region large model. Then the combined model is fine-tuned with large objective for few epochs. The second proposed method is language model integration via multitask learning. The motivation is to use unpaired text without audio during training last model. To do so, the author sets the last context vector to zeros when using unpaired text. In other words, they disable the last encoder when there's only text. As a result, there are two training tasks, ASR and language model training task, sharing the last model's decoder. In this section, we present results of fusion approaches and proposed approaches. The performance and scalability of fusion approaches were evaluated on 5 tests: switch bar, go home, Google Voice Search, and dictation. Google Voice Search and dictation are used for scalability evaluation. Also, the authors evaluated the fusion approaches in the presence of second pass rescoring. And lastly, they evaluate their proposed method on switch bar and go home sets. Firstly, fusion approaches were evaluated on switch bar and go home. The results show that all methods improve over baseline large model. The shallow fusion is clear winner. In the third row, The shallow fusions achieved best word error rate 15.6 on switchboard and 26.6 on go home. Secondly, scalability was evaluated on Google datasets. The shallow fusion is the best performer again. 5.3 on voice search and 3.7 on dictation, although tied with cold fusion on voice search dataset. Diffusion has no to unnoticeable gain over baseline, indicating that deep fusion does not scale well. While shallow fusion and cold fusion have very similar top 1 word error rate on Google datasets, we can investigate the quality of top 8 to better understanding the strengths of each approach. The result shows that second pass rescoring has no effect on shallow fusion, but cold fusion word error rate drops from 5.8 to 5.0. This suggests the improvements provided by shallow fusion are redundant with the benefits of the second pass rescoring. While cold fusion improves quality and diversity of top 8 hypotheses. In this slide, we present the performance of 2 proposed methods. The first one is the multitask learning approach. This approach achieves 17 absolute word error rate on switchboard and 27.5 on go home, which yields minor gain over baseline large model. However, it introduced no new parameters. The second approach is to use language models as an additional decoder layer. This approach is comparable to deep and cold fusion on switchboard, achieves 16.3 absolute word error rate. In conclusion, in this paper, a comparison of 3 fusion approaches was presented. For first pass scoring, shallow fusion performed the best. Cold fusion produced lower oracle word error rate among the top 8 hypotheses and outperforms shallow fusion at the second pass rescoring on Google Voice Search. Deep fusion has no gain over baseline large model on Google datasets, indicating diffusion cannot scale well. Among the proposed methods, using external language model as lower layer of decoder is comparable to shallow and cold fusion on switchboard dataset, suggesting that further investigation may be fruitful. Thanks for your attention.